Assalamualaikum and good afternoon. Today is our reference Zemi, which I will present to you. I present and explain to you about our paper from a Scopus journal, which is Q1 Scopus journal, which title of Driving Style Recognition based on electroencephalogram data from a simulated driving experiment. The author is from Wuhan University of Technology in China. The outline of this journal is introduction, materials and methods, result, novelty and limitation of the study, and conclusion. For the introduction, driving style is a very important indicator and a crucial measurement of drivers' performance and ability to drive in a safe and protective manner. If the driving style can be recognized by some appropriate classification methods, much attention could be paid to the driver with dangerous driving style. In most previous studies, drivers' questionnaire data and vehicle objective driving data were utilized to recognize driving style. However, these methods were indirect or subjective in driving style evaluation. In this paper, a method based on objective driving, they got from simulated driving, and electroencephalography (EEG) data was presented to classify driving style. In this research journal, they will classify the driving style into three, which is aggressive, moderate, and conservative. The result imply that different driving styles were related with different driving strategies and mental states, and suggest the feasibility of driving style recognition from EEG pattern. For this experiment, 30 participants were selected and all the participants have a driving license. There are 21 males and 2 females. The mean age is 23.9 plus minus 1.6 years. And all the participants have average driving experience of 2.9 years plus minus 1.7 years. The figure on the left shows that a simulated environment designed using Unity 3D, and the right figure shows the experimental setup for this experiment. The simulated environment was developed is a 7 km square road, which is contained of 2 consecutive S-shaped curves, 2 curved roads with radius of 20 meter, and 7 other curves in a mountainous scenery was applied. Okay, the participant was tasked to drive the vehicle in 4 laps, and between the lap, they will brake for a few minutes in order to avoid fatigue. The participants were asked to pay attention to the traffic sign and the real time speed of the vehicle and drive according to their driving habit and style in daily life. The speed limit for this experiment is 60 km per hour. You can see in figure 1b shows that the participant drive in the simulated environment by controlling a steering wheel from Logitech G29, and the EEG data were collected using Biopack MP150 system, which is a 16-channel EEG data acquisition device. This is a flowchart for the EEG based driving style recognitions. You see on the left side is a flow for the driving style recognition based on driving data. On the right side is a driving style calculation based on EEG data. Now we focus on the left side first, which is driving style calculation based on driving data. During the experiment, the data such as velocity, total time of driving, number of lane excursion, angular velocity of steering wheel, number of collision, angular acceleration, rotation angle of the steering wheel were collected in order to classify the style of the participant. After all the features are excited, the dead score are calculated, and then from 7 features, seven features or 7 dimension data, they reduce it to 2 dimension data using PCA, and then use K-means in order to classify into 3 diving style, which is aggressive, moderate, and conservative. Okay, and then we focus on the driving style dimension based on EEG data on the right side. Is the raw data extracted using EEG data acquisition device, and then filtered it in order to reduce noise and artifact contamination. And then from the processed EEG data, 8 dimension EEG features were extracted, and then from the 8 dimension we reduce to 2 dimension using FDA, and then the classification of the driving behavior using SVM. For the driving data analysis, 7 variables are collected during the experiment, which is steering wheel rotation angle, angular velocity, angular acceleration, total driving time, vehicle velocity, the number of accident or collision, and lane excursion. Data then averaged and standardized using Z-score method, and then K-mean algorithm used to classify the driving behavior. For the K-mean algorithm, there are several steps used in order to classify or cluster the driving behavior. First, initialization, then calculate the square equidistant distance, and then they assign each observation to the cluster whose centroid is nearest, and then update the cluster centroid based on new observation cluster. Step 2 to 4 are repeat until there are no further reassignment of the observation. For the EEG data analysis, there are several processes in order to classify the data. First, pre-processing. Second, feature extraction, and third, classification. For pre-processing, the whole EEG data acquired in each task is downsampled to 512 Hz, and then 4 EEG focusing band, which is delta, theta, alpha, and beta are extracted, and then independent component analysis (ICA) was utilized to decompose the filtered EEG data into several components, and the components caused by the artifacts such as movement, blinking, and muscular tension were identified and removed. The bad channels were detected and replaced by the average of 2 neighboring channels. Finally, the EEG data was re-referenced to the average reference to reduce the forward model error of each channel. This method is called average reference montage. For second stage of EEG data analysis, which is feature extraction, the EEG data was converted into frequency domain, and then the amplitude of the EEG signal in delta, theta, alpha, and beta band were obtained by using FFT, and power spectral density (PSD) in these 4 bands were estimated using Well's method. Each participant FFT and PSD were integrated to generate an 8-dimensional feature vector. Then the features vector were reduced to 2 dimensions using LDA in order to simplify the calculation. And next, SVM training process and improving the final calculation accuracy. Last stage of EEG data analysis is data classification using SVM. Initially, there are 8 features used in order to classify using SVM, but in order to reduce and simplify the computations, the author used LDA and reduced the features to 2. There are 3 classification class for the EEG data analysis, which is aggressive, moderate, and conservative. This is data for the driving data classifications. There are 7 driving variables used to classify the driving behavior. The driving variable are velocity, total time of driving, lane excursion, number of collision, angular velocity of steering wheel, angular acceleration and rotation of steering wheel. You can see here, okay, this is the mean value for the velocity data, and then for yeah, so the value here and here are the mean value for each driving variable, and the value here, here, and here are standard deviations of the driving variable. From this data, the author used analysis of variance and ANOVA to indicate indicates and differentiate the driving behavior of each participant. There are 3 classification used by the author. First, aggressive, moderate, and conservative. The aggressive group has the most accident and aberration, including lane excursion, collision, and largest rotation angle, angular velocity, angular rotation of the steering wheel, and faster vehicle velocity. It shows that the aggressive group drive the vehicle more aggressive and dangerously. This is the result for K-mean based on driving data. The driving data was clustered into 3 clusters using K-mean algorithm, which corresponding to 3 driving styles. This data is randomly selected in order to classify the driving behavior of the participant by using data from the driving variable as shown in table 1 before. This is the result for power spectrum of different driving style. We can see that in figure 4 showing that average PSD power spectral density of each EEG data in each group. You can see in theta band, which is 4 to 7 Hz. This part, the aggressive group has the highest PSD among 3 groups, while in theta band, which is 13 to 30 Hz, 13 to 30 Hz, okay, in this range, the aggressive shows that the aggressive group had lowest PSD. The conservative group PSD increased along with an increase of frequency and was highest in the alpha band, which is in 7 to 13 Hz, which possibly implies that conservative driver had more relaxed mental state. In Figure 5, shows that power topographic map for 3 driving style in 4 band. In band 1, 0.5 to 7 Hz, the aggressive group has significant higher PSD value in left temporal area, which is this part, than the conservative group. The aggressive group has the highest PSD in frontal area in band 1. This result indicates that aggressive group has highest theta-beta ratio in the frontal area compared to other two groups, which is moderate and conservative. The concentrated brain activation area over parietal area, which was related with association of sensitization for the conservative driver. You can see this part. Okay. It seemed that conservative drivers were more inclined to the proactive driving state, which was associated with a better anticipation and active use of ongoing information, and a more proactive planning for the future response. The table 2 shows the confusion metric for the SPM model. The average confusion accuracy is 80%, and the calculation error varied from 77 until 84%. Novelty and limitation for this study was the traffic scenario was relatively simple without considering multiple driving scenarios such as traffic jam. The changes of driving style under different driving scenarios should be analyzed in the future for future works. The complexity of the scenario will affect the degree of driving difficulty. Specifically, the format of the turning was related to different driving style and brain dynamics. The cognitive load and simulator-related side effects were not considered in these studies. The participants may have been biased because the participants are selected in young age of groups, and they have short driving years, and the selection of the participants also unbalanced, which is the number of male participants more higher than female participants. For conclusions, the author hope that this method can be used to monitor and detect dangerous driving style. And second, the author hope that this system can use in order to initiate the warning procedure in order to reminding the driver to adjust his or her behavior if the driver drive the vehicle dangerously. Also, the system can be used to help or take over the vehicle when the driver drives dangerously. Lastly, the driving style recognition method can also be utilized to improve driving experience and comfort. Thank you for your time, and hope you can get something from this presentations, and we are open for Q&A session.